Welcome to solverfy.
There's a very long cylinder with charge density that goes as rho naught r squared by r naught squared. The radius of the cylinder is r naught, and we want to find out the field around it. Let's say we are looking at a cylinder at a distance r from the axis. We expect the field to be in the radial direction because of the cylindrical symmetry of the question. So we draw a Gaussian surface that looks something like this. I've magnified into the picture here. The Gaussian surface looks something like this. It's another cylinder inside our cylindrical rod which shares its axis with the cylinder. We know that this distance is r. So we expect the electric field to be radially outwards, which means and depend only on the distance from the axis because of the cylindrical symmetry. So the electric field will be the same all over the curved surface of the cylinder. Also, the electric field will be perpendicular to the two circular planar surfaces of the cylinder, the two faces. So the flux there will be zero. Hence, the flux, which is electric field times area, will be electric field times the area of the cylinder is simply the circumference times the length of the cylinder. Let's say the length of the cylinder is L, which gives us 2 pi r times L. Now this we know by Gauss's law is equal to Q enclosed divided by epsilon naught. So we need to find the charge enclosed. The charge enclosed will simply be integral rho dV, which will be integral rho. We integrate this using cylindrical coordinates, and we write dV as, we know that rho is rho naught r squared by r naught squared. We write dV as 2 pi r dr into L. This integral we carry on from 0 to r. Now this is an r squared dr form, r cube dr form, which will give us r power 4. So the answer turns out to be 2 pi rho naught by r naught square L into r power 4 by 4. This is simply pi rho naught L r power 4 by 2 r naught square, which means the electric field will be, by equating this to, now the electric field times area, which is 2 pi RL, will be equal to charge enclosed by epsilon naught. Charge enclosed is pi rho naught L r power 4 by 2 r naught square divided by epsilon naught. From this we get that the electric field is rho naught r cube divided by 4 epsilon naught r naught square. Now, for any point outside the cylinder, let's say this distance is r, we consider another cylinder. We do the same kind of flux derivation, and we get the flux to be 2 pi E into 2 pi RL, where L is the length of the cylinder. But the charge enclosed will simply be all of the charge within the cylinder. So that is integral from 0 to r naught rho dV. We know that rho is rho naught r square by r naught square. dV is 2 pi RL dr, which gives us charge enclosed is equal to pi rho naught L r naught square by 2. So we get the same thing as the last time, but instead of r, we have r naught. Again, using the same formula, that flux, which is E into 2 pi RL, is equal to charge enclosed, which is pi rho naught L square r naught square by 2 epsilon naught, gives us electric field is equal to rho naught r square r naught square divided by 4 epsilon naught r. Also remember that the electric field direction will be radially outwards. That's it.